So we're on page 4, and example 6, we are looking at an elastic collision. A ball at rest is struck elastically by another ball, which is 3 times as massive. The larger ball proceeds in the same direction at half its original volume. Find the velocity of the smaller ball after impact. So first thing let's draw a picture. So we have a smaller ball, mass m, and it is at rest. Then we have a ball which is 3 times as massive. And it comes in with a certain velocity. After we have both of them, and it is an elastic collision, so they are going to hit and they are going to bounce apart. So here's the first ball, here's the second, more massive ball. What it tells us about the larger ball is that it proceeds in the same direction at half its original velocity, 1/2 v. We want to know, find the velocity of the smaller ball after impact. And so we are looking for the velocity of this ball. Now we're not going to use the letter v to solve for this velocity because we already have v in this equation, and it's going to disappear if we use v, and it might mess up the whole situation. So let's stick with x here. Don't use v for the unknown. So let's go ahead and put this into our law of conservation of momentum formula. So before, we have a ball of mass m with a velocity of 0. Plus, we have a ball of mass 3m with a velocity v. Now you'll notice that I didn't make this velocity v negative. I just left it as a positive. It's the only thing moving in its direction to start with. Both things are moving in that direction at the end. You could make it negative v if you want, and you could try it out, but you're going to get the same answer either way. And that's why this one is positive and not negative. After the fact, so the smaller ball of mass m moves off with a velocity of x. Again, I made v going left positive, and so x is not going to have a negative sign attached to it. Plus, we have the 3m ball, the ball of mass 3 times, and it is moving at 1/2 of its original velocity. So this is 0. This is 3 times m times v. Here we have mx, and this is 3/2 times mv. So what I'll do is I'll just get rid of this 0. So the easiest way to take care of this and solve it is to just double everything, and that gets rid of this fraction. So if I multiply this times 2, and this times 2, and this times 2, so we're going to have 3mv, 2mx, and this will be 6 mv. Not a required step, but it makes it easier. So then I'm going to subtract this 3 mv to the other side. So we have 6 mv minus 3 mv equals 2 times mass times x. And then you solve for it and you find that x equals 3/2 v. And so to write this as a sentence, the small ball's velocity is 1.5 times the big ball's original velocity. And just to underline some things, the big ball's original velocity includes velocity, which is a direction. And so by saying this, we have implied the direction. Example 7, now for a different type of collision. A cannon of mass 4,000 kilograms fires a 20 kilogram cannonball at a velocity of 100 meters per second. Find the recoil velocity of the cannon. And for these, we're going to draw the picture still. Doesn't need to be extremely detailed. So here's a picture of a cannon. Here's the cannonball. So the cannon itself is 4,000 kilograms, and the cannonball kilograms. Now this thing hasn't been fired. The cannon is sitting still. The cannonball is at rest. The velocities are 0, and that means the total momentum here is 0 because both the velocities are 0. So after the fact, let's draw our after picture. Here's what happens. So the cannon fires the cannonball. The cannonball is now moving at 100 meters per second. And this cannon is not going to be sitting still. You know, a lot of cannons are on wheels and they will roll back, or a lot of them have some sort of a spring system to take the recoil. If it were maybe bolted to a ship, the entire ship would recoil a little bit, but then you're looking at the mass of the ship. This cannon is one that maybe is just on wheels. And it's going to recoil, which means it's going in the opposite direction. And we're just going to call that velocity x. Since the momentum was 0 in the beginning, the total momentum at the end also needs to be 0, which just goes to say that it obeys the law of conservation of momentum. So the formula here, the mass of the cannon times the velocity of the cannon plus the mass of the ball times the velocity of the ball. These are the before conditions. And this is equal to the mass of the cannon plus the velocity of the cannon prime plus the mass of the cannonball times the velocity of the cannonball prime. So let's use our real numbers here. The mass of the cannon is 4,000, and its original velocity is 0. It's at rest. The cannonball, mass 20, velocity is also 0. So now for the mass of the cannon, it is still the same, still 4,000. The velocity after, with the velocity of the cannon prime, is x. That's the recoil. That's what we're looking for. Plus the mass of the cannonball is 20. And the new velocity of the cannonball is 100 meters per second. So everything in the original or the before conditions is 0. So 0 equals 4,000x plus 2,000. So subtract it over. Negative 2,000 equals 4,000 times x. And x equals negative 1/2. And that's meters per second, which is to say negative 0.5 meters per second. So as far as the direction goes, the negative does imply some sort of a direction, but let's make a definition here. So the definition is, let recoil mean in the opposite direction. And so what you could say is that it will recoil at 0.5 meters per second. So if we look at the ratio of the masses, the cannon to the ball, cannon mass 4,000, ball of mass 20. The ratio here is 200 to 1. The ratio of their speeds, the ball to the cannon, here's the ball, here's the cannon, is also 200 to 1. So the ratio is pretty big. You want to make sure not to fire a gun which is not very much greater in mass than the bullet. There's a reason that a cannon is so massive. If the gun and the bullet are the same mass, their recoil would be equal as well. So if this cannonball were 20 kilograms, as it was, but the cannon was 20 kilograms, then they would have equal velocities in the after, just in opposite directions. The recoil of that 20 kilogram cannon would be equal to the speed of the cannonball. You wouldn't want to be behind that. example 8, a father, mass 90 kilograms, and his son, mass 40 kilograms, are on a frictionless ice pond. To escape, they push against each other, sending the son off at 1.8 meters per second. At what speed does the father travel in the opposite direction? So they're on a frictionless ice pond, and here's the problem with being on a frictionless ice pond. You can't take steps, you can't walk, because the pushing back of your foot requires friction to propel you forward. So you can't just walk off, and you can't just lay down and scoot off, because if you're going to pull yourself with your arms and legs, it requires friction. So there's no way off here except for this scenario. So let's draw a picture. You can use the situation of the circles if you want for the picture, or you can actually draw a picture with stick figures. So for this one, I'll draw this differently. So here's the dad, here's the son, and they're about to push on each other. Father is 90 kilograms, son is 40 kilograms. And they're going to push as hard as they can, which means that the father is moving in this direction, and the son is moving in this direction. Since the son has a smaller mass, he should be moving at a faster velocity. And again, their masses didn't change. So the mass of the father times the initial velocity of the father, mass of son times the initial velocity of the son, equals the mass of the father times the new velocity of the father, plus the mass of the son times the new velocity of the son. Same formula, we just replaced A and B with F for father, S for son. Doesn't change what we're doing here. So let's put in some numbers. Father's mass is 90. Initially, they are at rest on a frictionless ice pond, 0. Son's velocity is 40, mass is 40, and the velocity initially is 0. Then they push each other. So we know a few things, and actually we left something out of our picture. The son is moving off at 1.8 meters per second. And so we are looking for the father's speed, x. So the mass of the father is still 90. New velocity is x. Mass of the son is still 40. New velocity, 1.8. So initially, the momentum is 0 for both of them. After the fact, we have 90x for the father, and we have 72 for the son. Solving for x, .8 meters per second in the opposite direction. But take a look at this. The question is asking for speed, which doesn't need a direction. And so with this answer, all we have to say is his speed is 0.8 meters per second. If it asks for velocity, his velocity is 0.8 meters per second in the opposite direction of the sun. But it just asks for speed. So let's think back to the paragraph above where we compared the ratio of masses and the ratio of speeds for the cannonball. So the original ratio of the masses, 90/40. Father's mass, son's mass. Remember the ratio of the masses, the cannon to the ball was 200-1. And then the ratio of the speeds, the ball to the cannon, so they were flipped. So the ratio of the masses, father over the son, equals the ratio of speeds, but the son is on top and the father is on bottom. And so this is how you could do it using the ratios, and it would have been really pretty fast. It's easy to mess up the ratios if you get them upside down. The law of conservation of momentum formula is longer, but it is more reliable. This next part is a mathematical proof of the law of conservation of momentum. I don't want to spend a lot of time on video talking you through it, and I don't want to place, a lot of emphasis on this. But what I want you to do is pause the video and go ahead and write this stuff down. And basically what happened is we took these three formulas, net force, acceleration, and Newton's third law, and we put them together. And so we moved time over and we changed some terms and everything works. So force times time is delta P, put time in here. Anyway, pause the tape and take a look at it, write it down, but I don't expect you to commit this to memory by any means, and I don't expect you to be able to do this on your own.